rejected. Yeah, it's more confusing.
Yeah, it's a confusing thing. You need to remember it. You need to remember it like less than
Yes,
less than reject, greater than accept. Less than important, greater than not important.
yes.
Less than important. When the p-value is less than 0.05, we say the feature is important. This point is very important. In this whole class, right? This table is very important. This particular table is very important. And then now we were talking about this p-value. And one more question I have is how this p-value is calculated by looking at individual column and target variable or total data, total input variables and target variable. Let me ask the question in a different way. Right, I have two columns here, input columns and salary, one output column. And when we calculate p-value, when the algorithm is calculating p-value, how is it calculating? By looking at all these columns and the salaries relation or individual column and salaries relation.
I think it is all.
It's
No, it is individual column and the target variable. That's the drawback with the p-value. When you look at p-value, right, it is always with individual column and the target variable. Okay, so I actually showed you something yesterday, right? I showed you something yesterday. Like, let me try to draw this again. This point is very important because some of the researchers, when they are writing papers, right, they are trying to take the p-value based feature importance scores and all that. That is not valid. Basically, if somebody knows the theory properly, whatever they are doing is not valid. Give me one. Let me draw this and again explain again. These things are important when somebody is doing the work and you need to monitor. Right, that time this is very important because they may show something. If you don't know the fundamentals, right, you may think like no, it is whatever they did is right. Okay, so let me draw this and explain. So when you look at this p-value, right, this p-value, how is it generated? Now this number, right, this number and this number are generated on do you hear any noise?
Yeah.
Kids playing?
Not that one actually.
Okay, let us. So here, right, when you say this number and this number, right, how is it got generated? Actual experience column, right, and actual salary column it took, right. It formed n number of equations, right, m number of equations, m number of records, and n number of features. Now here only one feature, one input feature. Okay, one output feature. So when I say n number of features, right, there I'm talking about input features. So it will form m number of equations, solve all of them at once, and find these coefficients. Okay. So after finding these coefficients, it will find the standard error, the t value and p value and all that. How is it going to calculate it? Null hypothesis. And what is null hypothesis for linear regression? No relation between experience and salary. Right? Experience and salary. When I say no relationship between experience and salary, this is the null hypothesis situation. In null hypothesis situation, how many times this coefficient is coming? That's what we need to see. That's the hypothesis testing or inferential statistic. In null hypothesis situation, how many times we are getting these scores or these numbers as coefficients in the equation? What are these numbers? 7882 plus 5171 into experience is the predicted salary. I will put it as pred sal. Okay. This equation is the predicted salary. If we are getting these coefficients when null hypothesis is true many times, that means this experience is not important in predicting salary. Even when, even when in null hypothesis situation, this is happening many times means there is not much importance. What is null hypothesis situation? No relation. When I say no relation, right, I can shuffle, right, I can keep the experiences intact and shuffle these salaries, or keep salaries intact and shuffle experiences and try to form the equations and find these coefficients. Again shuffle, form equations. Why am I shuffling these? Null hypothesis situation is saying no relation. When there is no relation, right, these coefficients should happen even when I shuffle it. Do you agree with my statement?
Yes, Rama.
So if it happens like that, then we say the null hypothesis is accepted. Is that correct?
Yeah, if many times or more than out of 100, more than 5 times if it is happening, these numbers are coming, then we say null hypothesis is true. Not significant. Whatever the relationship, actual relationship is not significant. Even though you shuffle, even when you shuffle, the same thing is happening 5 times out of 100. That means actual relationship is not significant. Okay. So to do this test, you always have to take one column, one input column and output column, and you are calculating the p-value. What is this p-value? Out of 100 times, how many times this is happening when null hypothesis situation is true, or when you shuffled it? If you have many input variables, right? Experience, age, maybe behavioral score, right? Each individual column you take and then try to do this hypothesis testing and find p-value. Got it? Got it? It is not as a whole.
Okay, this is just to identify whether an attribute or whether a column is
Important.
useful to predict.
Important or not. This p-value is actually defining that, right? This p-value is less than 0.05. This feature is important. This feature is important. If it is greater than 0.05, this feature is not important. If when I say it is greater than 0.05, the null hypothesis situation, this coefficient is happening many times. When you shuffle the data and try to build the model, it is happening many times. More than 5 times out of 100, more than 5 number of times it is happening. We took alpha, the threshold, at 5. We can change it. We can change it. Our statisticians generally change it depending on the business situation, but in machine learning, right, we take 5, 0.05 as the alpha value. Got it? Got it?
Yes, Rama. So why actually we are trying to keep intact one attribute, the input attribute, and we are trying to change the output.
Yeah, your question has got answered. Just think about it one more time. Let me repeat the statement. When you think, right, you will get it. I am saying null hypothesis situation is true. I wanted to find the coefficients when null hypothesis situation is true. What is null hypothesis situation? No relationship between experience and salary. When I say no relationship between experience and salary, I can shuffle. Both I can shuffle, right? But I am fixing one and shuffling other because I wanted to see when I shuffle randomly, I may get the same relationship again. I don't want to create that. It may happen rare, but there is a possibility, right? If you shuffle both, they both may come to the same state where the original data is. Do you agree?
Yes. My question is so we are keeping one thing intact and we are changing the other one to identify whether our hypothesis is true, even if we are changing the values.
No.
Just to identify whether that feature is significant or not.
Yeah. So it is like in sampling distribution of means, what you are doing, you are taking multiple samples from the same population, right?
Yes.
But here it is not a sampling distribution. It is not about means. It is about the coefficient of the equation, right? You need to, when you have to calculate p-value or z-score of this number, a t-score or z-score are same. I said t-score or z-score are same. Formula is a bit different. The variance formula is actually n minus 1, and in the z-score, the variance formula is divided by n. That point is clear, right? T-score and z-score are same, right? So to calculate t-score or z-score for this number, you need to have multiple coefficients, right? Multiple coefficients. Do you agree? Multiple equations. Do you agree? Did you get the statement? Did you get that statement? Yes? No?
Can you please come again?
So to anytime you wanted to calculate t-score or z-score, what you need? Z-score I wanted to calculate. What is the formula for z-score? R t-score. If it is a population, I'll say Z. To a sample, I'll say T. In a layman's terminology. What do you need to calculate?
Multiple samples.
The
Mean of
formula is
multiple
that
samples.
x minus mu divided by sigma, right? You need to calculate mu and sigma. To calculate mu and sigma, you need multiple equations, multiple numbers, multiple these numbers, right? For this number, I calculate t-score. For this number, I calculate t-score. Do you agree? Right here, x is for this x is 7882 minus mu divided by sigma. For this 5171 minus mu by sigma. This mu is different, that mu is different. Maybe this is mu1, this is mu2, sigma1, mu2, sigma2, right? So to calculate mu1 and mu2, I need many of these numbers. How do you get those numbers?
Okay, so you are taking one thing, a single thing, and you are trying to shuffle.
Yeah,
and,
right.
and then make it a kind of replication of different samples, kind of stuff.
Yeah, I took experience, original experience and salary, built a model. When I say built a model, forming equations, solving them, finding these coefficients, right? That's first step. From next time onwards, right? The model internally, the OLS model internally, keeping one column fixed and another column shuffled, because in null hypothesis situation, null hypothesis is saying there is no relationship. When there is no relationship, show me that these two numbers are happening very frequently. That's what I am challenging, right? When null hypothesis situation is true, or when there is no relationship, when I say there no relationship or existing relationship is not significant, right? Null hypothesis is saying what? Existing relationship is not significant. So I'll keep one intact, other shuffle, right? That means I changed the data, right? If existing is not significant, when I changed the data, whatever values I got when the original data was there should come very frequently. Are you getting the point?
Yes.
Huh?
Yes.
Getting it right. Null hypothesis is true. That guy is challenging, right? No, there is no relationship. Whatever you said is not true. And I say, yeah, I accept whatever you said is right. Right? I accept whatever you said is right. Let us experiment. What is the experiment? We are actually shuffling the data. Anyway, you said no relationship. So I'll shuffle the data. Show me how frequently these coefficients are happening. Right? I did many times. I have got many numbers. Using those numbers, I calculated mu1 and sigma1. I calculated t values, and using t values, I calculated p. That one we did it in rat example, right? When you know the z score, right? 1.05 z score is around -3. Do you remember that? 1.05.
Yeah.
Right? Around -3 means 99.7% of the times it is not happening. That means that number is very rare in null hypothesis situation. That means whatever relationship is significant. Right? 99.7% of the times it was not happening. That means very rare. If it is happening, 68%, right? Maybe around 70% time, or maybe 94%, right? 94, the Z score is 94.94. Then also we'll accept because it's more than 0.05. Got it?
Yes.
Right.
That point I got it, but the exercise, as we said, we are taking one input and one output, and we are trying to change, in this case, experience and salary. We are trying to change the salary, keeping the experience intact. So we are doing this exercise to actually find whether the salary is significant or no, the experience is significant to find.
T-score and p-value. By using T-score and p-value, we are actually assessing whether it is significant or not.
Yeah, that I understand, but we are keeping the one attribute same and the other attribute we are changing it, and we are going to do that multiple times. Multiple times we are going to shuffle, and multiple times we are going to calculate these coefficients. So this exercise we are doing to identify whether that feature is significant in the prediction or not.
Yeah.
Is my understanding correct?
Your understanding is exactly right. But when you shuffle and do all that, ultimate result is going to be the p-value. Based on p-value, you are making decision whether it is significant or not. Yeah, your understanding is correct. And this is all done by OLS algorithm. No need to do it. When you say fit right, it is actually doing it and giving you these numbers. And I say summary, right? I got these numbers. Did I calculate these? No, right?
No.
Right? So algorithms will do. You need to understand the concept because you have a hammer and an axe and a wrench. Which one to use where you should know. Then only you will be able to use it. If you give all these three to a kid, right, he will be using hammer in place of wrench and wrench in place of whatever, right? So it is like that. There are many tools in AI. We need to understand which one to use where. And basically my point here is that p-value based feature selection is not that good, because it is actually looking at one column and the target variable only. When I said, when you take multiple columns as input and one output, there will be interrelationship between the columns and they will have effect on the target variable. The interrelationship will have effect on the target variable. If you don't consider interrelationship, right, we may not get the good features and good results as an outcome. Okay, got it?
Yes.
So the p-value based selection is not that good. That is the point I wanted to explain. And again, this point of looking, one column and the target variable, trying to calculate p-value. This we are going to discuss this in, linear regression assumptions again. So I'm just trying to, pave some basement there. Okay. And one more thing is we can do feature selection using p-values, right? Because p-value is greater than 0.05, you say that feature is not important, and less than 0.05, you say the feature is not important. So I will talk about that. There are approaches like forward selection, backward selection, and mixed selection. Three concepts. Previously, right, in 2018-17 time frame, people used to ask this in interviews. Now they are not asking. Okay, because 99% of the times p-value based feature selection is not happening in the industry right now. We have mathematical machine learning approaches. I will show you regularization and the random forest kind of algorithms will give you importances. Using those you will select best features. I will show them, but the concept I will explain you after maybe Monday or so. Okay, so for now you just remember this and we'll come back to this maybe twice in the course. Okay, so that is one thing we understood, and then we understood like the confidence interval, right? These numbers are the ones, this coefficient may oscillate when you change data, may oscillate when you change data. How did we got it? By shuffling the data and all that way we did the experimentation, right? So we got to know the 95% confidence interval. This is at -2 z-score and this is at +2 z-score, right? That's where 95% confidence interval. 2 z-score, this is +2 z-score. Okay, and we looked at R square score and adjusted R square scores. Let me repeat this. Yesterday I went a little faster. So after building model, right, we can use the model.predict method to predict the salaries for the experiences. Right? On the train set only, I am actually calculating salaries. So these are the predicted salaries. Right? So there is gap between the predicted salary, actual salary, and the predicted salary. There is a gap between. That gap is called as error. You calculate that and you call that as error or residual. And we generally do squared error because we wanted to sum the whole errors and calculate one error for the total data set. When you don't square, these negatives and positives may get cancelled and you may not get the magnitude, the error magnitude not properly. And when you do squared errors, the sum of squared errors, right? The sum of squared errors should be close to 0. But when the output value, is in decimals, is between zeros and ones, your error may also, the squared error may also come close to 0, but the model may not be working well. Even when the model may not be working well, the squared error may come close to 0 when the target variable is between 0 and 1. Did you get this statement? Any questions? Any questions? I actually showed you yesterday. I don't know whether Seshiram looked into the video or not. That's why I'm actually stopping a little bit. You looked into it, right?
Actually, last 20 minutes I did not.
Okay. Maybe last 20 minutes is the class.
Yeah, I tried. I was actually out of station and came back at 1 o'clock and still tried to spend some time, but
Yeah,
I didn't.
that's a good thing. That's a good
Yeah,
thing.
I, I
Yeah,
will.
try
I
to
will actually try
right,
doing
yeah,
that.
try to look at it maybe in the evening one more time. Right. So the point here is the salary here is a big number, and when you predict also a big number comes and the residual is going to be a big number. But if your target variable is a small number, right? Maybe I actually took the thickness of a cloth. Thickness of a cloth is going to be in 0.0 numbers, right? If you are trying to take the material, properties of the material, cloth material, and then trying to predict the thickness of the cloth, right? And the data set is going to be material properties are going to be input variables, and thickness is going to be the output variable. And you will take multiple records, and then you build a model. The output variable is values between 0 and 1. The predicted value also is going to be between 0 and 1. When you take the difference, that is also going to be 0 and 1, between 0 and 1. When you square it, it is going to reduce even more. 0.1 square is 0.01. 0.01 square is 0.001. So the squared error should not be a proper measure, appropriate measure when the y value is between 0 and 1. The y value is a small number. You should not take squared error as the metric to measure the accuracy of the model. Why? Because squared error should be close to 0 to say the model is working good, should be bigger number to say model is not working good. So the solution is R square score. What is R square score? This is the squared error I was actually talking about. Y and y cap. Y cap is the predicted value, y is the actual value. We actually calculated the residual sum of squares. I have actually shown you here maybe 5 records, but for 32 records I will calculate the squared error, sum all of them. That is squared error. And there is one more error called as total sum of squares, right? Total sum of squares. This is not error, but this is total sum of squares we call it as. It is y minus y bar. It is y bar means mean of the target variable. This is like you used an intelligent model and predict and tried, and you actually took the mean of all the records, all the y values, and said that is the prediction. You said that is the prediction, and then you try to calculate the error. So this is actually dumb model. the R square score is going to compare the values between the dumb model, the metrics between the dumb model and the intelligent model. If TSS together, my model prediction is as good as the average of all the target variable values. If these two are close to each other, my model, I actually did a lot of work to do cleanup and all that, and then built a model. And ultimately, I'm getting a number, which is close to TSS after, trying to do assessment. That means the numerator is going to be 0, so R square is going to be 0. If R square score is 0 or close to 0, the model is not working well because it is as good as the prediction is as good as the average of the target variable. If this is close to 1, if RSS is close to 0, right? And even when the values are like the target variable is a small number, TSS is going to be a big number, and RSS is going to be very small number when compared to TSS. When you have a small number compared to TSS, right? The numerator and denominator are almost going to be same. Then you will get a number close to 1. So if R square score is close to 1, the model is working good. The R square score is close to 0, the model is not working good. Here, when you look at R square score, it's always going to be between 0 and 1. Okay, so you have perfect scale there. You know whether the model is working good or not working good. 0 means not working good, 1 means working good. So I have a question. Is there a possibility that R square score comes negative? Is there a possibility that R square score comes negative?
No.
Anybody agrees, disagrees with
It may come negative when TSS is 0.
Yeah, TSS is less than or TSS is 0. TSS can also be 0 when all y values are same, but that is not a model actually. No need of building a model there. But sometimes what happens is your model works so worse that it is bigger than TSS. Sometimes it happens. When you build models, right, you get negative R square score. When you are getting negative R square score, you did something fundamentally wrong. You should actually go back and check the total code. Okay. So there is a possibility, but it should be between 0 and 1. Most of the times it will be between 0 and 1, and it should be between 0 and 1. Okay. So that is, and it will never be greater than 1. But negative numbers can be bigger numbers also when the model is not working well at all. Okay. The next thing is adjusted R square score. The problem with R square score is when you have 10 features and built a model, you may get a 0.9 accuracy. If you add 10 more features and build a model, right, or maybe 2 more features or 3 more features and build a, when I say features, input features, right, when you add 2 more, 3 more input features and build a model again, you may get a score a little greater than 0.9, even though the newly added features are not important, right? So x1 to x10 are there. Built a model, we got 90% accuracy. What is 90%? 0.9. Okay. And I added 4 more features like x11, x12, x13, and x14. They are not really important. Some from somewhere else I just maybe randomly generated numbers I added to the data set. Even then, the 90 becomes 91%. Because the R square score's disadvantage is that. So to avoid that, right, there is a mathematical manipulation here. Even when you add more features, this here n is the number of features, m is number of rows, right? Number of samples means number of rows, n means number of features. Even when you add more features here, what we are doing in the denominator, m minus n, we are 100 record, maybe 1500 records and 10 features. You calculate adjusted R square score, you get some number. 1500 records, 14 features. What will happen? The denominator will reduce a little bit, right? 1500 minus 14. 1500 minus 10. Initially it was 1500 minus 10. When you added more features, right, it is 1500 minus 14. The denominator is reduced. That means this number will become a little bigger, right? R square score may become a little bigger because you added more features, right? And the denominator is small, it may become even bigger. And we are actually subtracting it from, so we are doing 1 minus here. So the numerator will become small, denominator will become small. So this is actually going to nullify that additional features effect. Getting it? This is not R square, this is actually R square score it is. So when you add four more features, what will happen? R square score will increase a little bit, right? We are doing 1 minus of it, right? So the initially it was 0.9, it is 9.1 now, right? 1 minus 0.9 is 0.1, 1 minus 9.1 is whatever 0.99, right? It reduced a little bit, and denominator also reduced a little bit. So the calculation is going to stay there, and 1 minus. So whatever the minute effect, it is getting added because of adding new columns in the R square score can be nullified using this formula. That is the adjusted R square score. Okay, if the R square score increased maybe 5 points from 90 to 95, this effect, this nullifying effect may not work that efficiently. Okay, this is just to nullify the minute effect got added by the new features. Getting it? It's a mathematical manipulation. Getting it? Any questions on the statements I made right now? Yes, no. I think we are good, right? So this, whatever I am actually talking right now is the thought process, basically. Yeah, you know, these formulas not big. This formula is not a big thing, or this formula is not a big thing. But when I'm looking at formula and actually talking about it, right? I'm looking at this formula and saying that an intelligent model, you know, prediction and my y values, and I am actually calculating error. A dumb model's prediction and my y value and calculating, and a dumb value model and intelligent model should not be close to each other. So I'm actually taking the formulas and talking in English, right? Business perspective, I'm actually talking. That kind of thought process you need to cultivate or, you know, inculcate to become a good data scientist or AI engineer, because we will see many formulas in our course. No need to remember. Even if you don't remember, that's fine. But when you look at the formula and, you know, the whatever are happening behind the scenes, right? You should be able to, you know, connect those dots and understand the way I'm actually explaining. The thought process should be there. Okay? Because I may explain 100 formulas, but in future, right, you may get 100 more. Who will explain that? You need to have this thought process. Okay? I think you got it. So can I move on?
Yes, Rama.
Yes.
So there are two more metrics for regression problem, where we are actually looking into regression problems metrics. Whether model is working good or not, that's what my question is. Right? By looking at this R square score, I should be able to decide whether model is working good or not. There are two more metrics called as mean squared error and root mean squared error. What is mean squared error? RSS divided by M, average of all the squared errors. Right? If you look at this, right? These are all squared errors, right? If you take average of it, right, you will get a variance kind of a metric. Right? How much deviation, right, between the minimum error and the maximum error, you will know by looking at this. Okay? On an average, right? This is like variance kind of. This is not mean, right? This is actually prediction. For each record, it's going to be different, but kind of, right? You can actually have some similarity there. When I apply square root, right, this is like standard deviation. Right? How much deviation is there in actual units of error? Okay? In squared units, the mean squared error will show you the variance. But on the error, right, if you look at the error, how much deviation is there? When you look at the minimum error and the maximum error, how much deviation? So if I calculate, you know, RMSE, did I calculate somewhere? I don't think I did it here. Maybe I'll do it in later sessions of the course. And when I look at RMSE, right, I can say When I look at RMSE, I can say the prediction is oscillating that much, right? So if for this particular model, if I get RMSE as 2000, right, what I can say is the prediction is 85,000. Maybe the actual value may be around 82,500 or 87,500. 68% confident. Got it? I'm actually going back to normal distribution all the time, right? Right? Did you get my statements? We'll actually see this practically in coming classes, but I'm just trying to induce some thought process into mind. If I talk some confusing concept, right, you will think about it. This guy actually doing something, right? So you will focus on it. That's the key there. Did you get what I'm actually saying? Should I repeat the statements?
Yeah, please repeat, sir.
Yeah, please, Rama.
So if you look at this RMSE score, does it look like standard deviation formula? Does it look like standard deviation formula?
Yes.
Yes, right. Instead of y bar, we have y cap here. Okay. So what are we doing here? We are taking the squared errors and taking the mean and applying square root. What are we doing here? Average of the squared errors we have taken and applied square root. That means it is average of the error, right? Average of the deviation, right? Average of the deviation. What is deviation? From actual value to predicted value. How much deviation, right? How much distance is there between the actual value and the predicted value? The deviation's average square root it is, right? First statement is clear. First statement is clear, right? What that means? When you make a prediction on an average, that much deviation is happening. Do you get this statement now? When you make a prediction on an average, that much deviation, RMSE much deviation is happening. Right? What is deviation? If I predict 85,000, if the RMSE score is 2000, right? The actual value may fall between 83,000 and 87,000. I am 68% confident. Now got it? Should I repeat or should I draw?
Yeah, understand.
Okay. So we'll come back to this again and again. Don't be worried, right? Even if you don't understand, don't be worried. So normal distribution and the 3 sigma rule is very important. It is the key. It is for AI, gradient descent algorithm, linear regression, logistic regression are the key. For statistical analysis, normal distribution, 3 sigma rule are the key. If you understand these, you are good. You are good for life in AI. Okay. If you don't understand, right, it may actually kind of lag. Every time you try to do something, it'll come in your way. Okay. So that is the regression problem, and then how to build a model and how to check the accuracy and different measures metrics. We will come back to these again and again. Okay. And I have taken multiple columns here. So previously what I did, only experience and salary. If you look at the model OLS, I took only salary and only experience and tried to build the model, right? Just to show you that, the graph and all that, right? Years of experience and salary. If I have one more column here as input, I'll get one more dimension here, third dimension I'll get. Z-axis or y-axis, right? And then this line will become a plane. I cannot show it, so simple example. And when we take the multiple inputs, right, to the OLS formula, you need to pass the output value, and the input value is concatenated by plus, and from which data frame it should be taken. Okay, experience plus lines of code and fit. Again, the same thing. It's going to format the equations, solve all of them once, and it will find the coefficients, And again, it actually found the p-value here. See this? The lines of code p-value is 0.7. Okay, the intercepts p-value is 0.3. What that means? Is this intercept important? Is this lines of code important in predicting the salary?
Sir,
So
before
lines of code is
answering,
important.
Some Grigar, you are saying something. Narendra said important.
yeah, what I want to ask is the lines of, when I say lines of code, it's basically coefficient of lines of code. Is that correct?
These are the coefficients. Yeah, let me
Lines of code is a
try.
feature.
Let me try to draw this. That's a good question. So ultimately, after building the model, after passing, the values, I've got an equation. Predicted salary, pred sal is equal to 5890 plus 5301 into experience plus 0.3081 into lines of code. Lines of code is the number of lines the person wrote the code. With experience growing, right, the number of lines of code will reduce, right? So it's a negative correlation, we call it as. So this is the equation. If a new record comes in, experience, 10 years, lines of code 10,000. Then I substitute this value and this value into these two numbers, and I predict the salary. Okay. So that is the equation. Is this the question you asked?
Yeah,
Right.
this is what I asked.
Okay. And now by looking at the p-value, which features are important out of these three? This is feature selection, we call it as in AI. Which features are important out of these three?
Experience and lines of code.
Experience and lines of code are important, right?
Yeah.
Narendra is saying experience and lines of code. Anybody agrees or disagrees?
Experience is important because it's less than 0.05.
Yes.
Yeah,
And
lines of code is more than 0.05.
What about intercept?
That is more than 0.05.
So, so these two are not important. Intercept and lines of code are not important. Experience is important. This model is saying, right? This particular model is saying. But in the previous model, right? If you look at the above model, it is saying intercept is also important. Experience and intercept both are important. Do you agree? Because p-value is less than 0.05. Narendra, you need to remember. Sorry, Narendra, you need to remember. No,
No,
you are getting
I am
confused.
thinking different, man. I'm
That
thinking
happens.
different.
That happens. You need to remember. Less than means important, greater than means not important. Okay. So it is saying that in this model, right, the intercept and experience are important. When I added a new column, right, new column in the input space, suddenly see this intercept is, it is saying intercept is not important. Leave, the lines of code we'll see later, but whatever is important is saying unimportant because of adding new column there. Got it? Got it? Got it? Because of this, additional column, this is called as interaction effect. By adding more columns, right? Some features which are important also may become unimportant because of the, the way the p-value is calculated. Okay. That's where when you want to see features are important or not, you should not be eliminating all the features which have got more than 0.05. You need to take the highest valued feature, eliminate it, then build a model and see how the p-value is changing. If the p-value is still greater than 0.05, then you eliminate it. Like that you need to go. That is called as backward selection. I'll show you maybe in a bigger example. Okay. So that is one point I wanted to highlight here, and one more point I was trying to highlight. I forgot. Yeah, we'll see. That is the, I think you got the gist of it. Now we move forward. Okay. So the next concept is we actually are done with the connectivity between the statistics and machine learning. Bad network quality. The network is causing poor call quality. Am I audible?
Yeah,
Yeah,
Yes.
audible, but the screen is, hanging for a few seconds sometimes.
Maybe I'll stop my, the video. That may actually improve quality. No, I am getting message saying that your internet quality is not good. Okay, so now it should be better. Okay, so the next concept is going to be bivariate analysis. Okay, so when we looked into the standard deviation, mean, median, mode, we were actually taking one column and trying to understand, right? One column only from the data. Do you agree? One column only, right? And when we did a linear regression, we were actually trying to build a model, find an equation, and then try to make a prediction. But before building a model, we actually have to analyze whether the feature is important or not. Okay. So when I say the feature is important or not, in input, there can be a categorical column or a quantitative column. In the output also, there can be a categorical column or quantitative column. On a regression problem, input can be categorical or quantitative, many inputs, right? But target variable is going to be quantitative only. What is quantitative? Numerical. Okay. On a classification problem, input can be categorical and quantitative, and target variable is categorical only. Right? If I want to if I want to predict a house price, right? There can be input variables that are numerical, right? Number of bedrooms, SFT area, right? And the number of floors, right? These are all numerical, okay? And then there may be quantitative or categorical, there may be categorical columns which are quality of the house and ratings given by other people, right? These are all categorical columns, right? So the input is like this. The price, we need to predict the same, price of the house. The target variable is quantitative only. In this case, right, you may have to see whether each individual column, each individual input feature is strongly related to the target variable or not before building a model. Okay, that is for that purpose, right? You need to do bivariate analysis. Take number of SFT area and the price, see whether they are correlated or strongly related or not. Right? Again, you take the quality of the house, good, excellent, poor, fair. These are the values. We call it as categorical because only 4 or 5 values will be there, or countable number of values will be there. If it is uncountable, right, or infinitely many, then we call it as text feature. Okay, we will handle text feature after we finish machine learning. Right? Till that point, I am actually going to concentrate on categorical columns only. So you need to see the categorical to quantitative relationship. Okay, so to find out the relationship between quantitative and quantitative, there is a concept called as correlation. There is a inferential statistic called as correlation, which actually tries to find out relationship between two quantitative variables. If you want to find out relationship between categorical to quantitative, right? ANOVA, analysis of variance, is the concept you need to use. If you want to find out relationship between categorical and categorical, when this will happen? On a classification problem, target variable is always categorical. Whether a person is going to buy or not, no. And if you take a picture, is that a car or a vehicle or a bike or a auto or truck? These are all different categories. So to categorical relationship, you need to understand chi-square test you need to do. Quantitative to categorical also chi-square test. There is a concept called as collapsing. Right? We do collapsing of the quantitative variables and then try to find out the relationship between basically convert into categorical and then do chi-square test. We are going to understand these inferential statistical tests, and we will be using correlation a lot. Chi-square and ANOVA very rare. Okay. So, but in interviews, right, they may ask. You know, some statisticians who are doing interviews, right, they may ask these questions. Any questions here on the slide? Okay, good. So now the bivariate analysis, and we need to understand covariance and correlation. You know, I said that between quantitative and quantitative, it is correlation test, right? So to understand correlation, you need to understand covariance. This is the formula for covariance. Again, covariance formula we are going to use in principal component analysis, one of the dimensionality reduction techniques. What is dimensionality reduction? If you have 10,000 columns, you want to reduce it to 100 columns without losing essence of the data. It is not that, you know, eliminate 9,999. You extract information from the data and create 100 columns. That is dimensionality reduction, we call it as. There we'll use covariance again. Okay. So the formula for covariance is xi minus xi bar into yi minus yi bar. What is x and y? Two columns. It can be input output or input also. Okay. Sometimes you may actually have to calculate covariance between input and input also. It is a measure used to analyze linear relationship between two variables. This is very important. The linear is very important. I actually highlighted, right? This covariance is going to identify find out the linear relationship between, or quantify the linear relationship between two variables. Okay. Also answers the question of how these two variables behave when paired. Okay. When they are together, how they actually behave also be understood by calculating this numerical value, statistic, a number, right? The positive value indicates that the increase in linear relationship. That means one is increasing, the other will also increase. So I generally take this example. Petrol prices increase, or the, you know, crude oil prices increase, all the commodity prices increases. Okay, that is a positive relationship. When you calculate, when you take different, you know, petrol prices of different days and commodity prices on different days, those are the two columns, and try to calculate mean of the petrol price and mean of the commodity price, any commodity, right? And then try to, you know, calculate, substitute into this formula, right? You get a correlation covariance value which is positive. Okay. And when the relationship is negative, right, you will get a negative number. Example for negative number is when petrol price increases, right, GDP goes down, right? GDP, gross domestic product, goes down, right? So take different days, you know, the petrol price, GDPs, two columns, try to calculate mean and then means of those and substitute into this formula, and you get a covariance which is negative. Okay, which is negative. So between two columns, there can be a positive relation or a negative relation. Positive relation means one is increasing, the other will also increase. Negative relation means one is increasing, the other will decrease. Some columns will not have any relation. They'll get, you know, the covariance close to zero. Okay. So when your input column and output column are chosen, there should be some correlation, either positive or negative. Okay. I made a statement here. When you choose a feature as an input feature, with that input feature to the target variable, there should be a positive covariance or negative covariance. Is that a right statement? Positive covariance means one increases, the other increases. Negative covariance means one increases, the other decreases. I am saying either one relationship should be there. Relationship should be there. Is that a right statement?
Yes.
Yeah.
Okay. So there should be some relation, either positive or negative. If there is no relation, right, zero, no, you not useful. It is like, you know, the same example I always take. You know, I am your friend. Whatever you say, I'll say, let's do it. right? Sometimes we both may go into some ditch, right? So that is not a good thing. It should be agreement or disagreements. Disagreement. That's where have some discussion and there is room for improvement. Right? Always disagree, always agree is also not good. So that's like so zero relation or positive negative relationship kind of thing. So same thing goes true in the data. Okay. So this is covariance formula, but the problem with covariance is there is no scale there. If you look at that R square score, between 0 and 1, the value falls and wherever you calculate. But when you calculate the squared error, right, there is no limit. Upper limit is not there, 0 and infinity. So we should not take measures or metrics which will actually have no scale, right, within some range. So the problem with covariance is that I've taken this data set, same, and then I calculated covariance between experience and salary. I've got 51,000. I've calculated covariance between experience and aggressive behavior score. I've got negative number. Experience and activity score, I've got negative number. But when you look at 55,000, it is a big number, positive number. When you look at these negative numbers, they are small negative numbers. Is the relationship too strong here or too weak here? We don't know. Whether it is negative or positive, it can be weak or strong. This is close to 0. We may think this is weak. It may not be true, right? Not be true because of the numbers present in the column. If you look at experience and aggressive score, experience, the values are between 0 and 15. Right? Aggressive score, the values are very small. When you substitute those values into this, right, you will get small number only. Got it? Got the problem? But when you look at experience and salary, right, experience is small number, salary is big number. When you take mean of the big number, you will get a big number, maybe around 20,000, 30,000. When you take differences between x and x bar, you will get big numbers, and you are actually summing up and dividing by 32, you will get big number, right? Depending on the data's magnitude, the covariance value will oscillate, and the strength is not clearly visible, right? In comparison with this relationship and this relationship and this relationship, which one is too strong, you cannot say. Is my statement right?
Yes, that's right.
Yeah. Anybody has got questions there? So this all, whatever I am talking right now, right, this is all thought process basically. This thought process again useful in machine learning algorithms also, right? Whatever I am speaking for last 1 month, right, this is all like pavement I am actually trying to do. This thought process you should get. Okay, so you have no guarantee that this is stronger and these two are weaker. So you will not be able to assess that. To solve this problem, we will use correlation. Okay, I have done a covariance. This is called as heat map. Heat map we call it. Okay.
So, sir, I have a doubt. Then why do we use covariance actually? So, if
We have some
can't determine it.
No, we have some places where we have to use covariance. I'll show you in the what you call it as the principal component analysis. You can use correlation also there, but it is used. So let me complete the class and then we'll come back to your question. Okay. Please give me like 10 more minutes. Okay. So here, that covariance only determines the direction but not the strength. That's what we understood based on the values, magnitude, right? You can calculate covariance by normalizing the data and then you calculate covariance, right? Then you can understand the magnitude also. So that's what we do when we have to calculate covariance. I'll come to that later. The covariance is maximized when two vectors are similar. Right? It is 0 when no relation. When orthogonal or negative when the points are opposite direction. So when they are orthogonal and okay. 0 when they are orthogonal. Orthogonal means perpendicular to each other. I'm actually talking vector terminology here. I'll talk about this later. Okay. So just read the statement and remember. Again, when you know linear algebra is split into 3 parts. I have explained one part before NumPy. I'll explain another part before gradient descent algorithm. I explain another part before principal component analysis. When we talk about principal component analysis, right, that time I'll talk about vectors and orthogonality and all that. Okay, just remember this statement for now. Okay, and yeah, I'll anyway cover it. There are notes and I'll not forget. So what I did is I took the employee dataset and calculated covariance heat map. How to do this I'll show tomorrow using code. Okay, covariance heat map we call it as. See this experience, salary, aggressive behavior, activity score and lines of code. Right, these are the columns here. Experience, salary, aggressive behavior, activity score, lines of code. Designation I did not took, I think. Yeah, designation is a categorical column, right? So you cannot calculate covariance there for that. Only numerical columns you can calculate covariance. On the Y also you see experience, salary. So to experience, 10 is the covariance score. Okay. To experience to salary, right? So to experience to aggressive behavior, the experience to whatever, right? And then salary to all. So if you look at this table, this covariance matrix, right? It's a symmetric matrix. When I say symmetric matrix, upper triangular values and lower triangular values are going to be same. This number is same. This number and this number is same. This, if you look at lower triangular matrix, right, that's enough. So between each feature and the other feature, we are trying to, it's like Cartesian product. Okay, and there is a scale on the, here it is showing. This color means close to 0. Green color means negative. Red color means positive, right? Positive, strong positive relationship. Salary and salary, you see how big this number is. Why did you got that big number? Between salary and salary, why did you got this big number? Can you see the number there? Why?
Yeah, of all the numericals, salary numbers are higher.
The numbers are in thousands, right? Thousands, that's where you got that big number. I'm just trying to check whether my point reached you or not. Okay, so this is called a heat map. And by looking at the heat map, right, you can understand the strong negative and strong positive relationship. Wherever the red color and green color is there is strong relationship between those features, and you can take those features and build a model. But covariance is actually showing you the direction only. To solve that problem, we actually do correlation. Correlation coefficient. What is correlation coefficient? Covariance divided by standard deviation of x into standard deviation of y. What we are doing is x minus x bar divided by standard deviation of x and y minus y bar divided by standard deviation of y. In this formula we are doing. When you actually standardize, it is called as normalization. Let us take an example here. Now, suppose that I have taken the maximum from the experience. Now, maximum is 15. Okay. Taken maximum from the experience and divided all the values in the experience column. What will happen to the values there? What will happen to the column values in there? Should I repeat the statement?
Yes, please.
I have taken this experience column and took the maximum value and took each value from the experience and divided with the maximum value. 15 by 15, 3 by 15, 6 by 15, 2 by 15, 5 by 15, like that. What will happen to the values?
We'll get negative values.
They will all come between 0 and 1, right?
0 and 1.
They'll all come between 0 and 1. That is one thing. Okay. And next thing, I take salary, maximum salary, and divide all the salary values with maximum. 85,000 by 85,000, 25,000 by 85,000, 36,000 by 85,000, 20,000 by 85,000, 37,000 by 85,000. What will happen to the values here? They will also come between 0 and 1, right? Right?
Yeah.
Yes.
Take all the numerical columns, take the maximum and divide the maximum with that corresponding column. Take the maximum here, divide all the values. Take the maximum, divide all the values. Take the maximum, divide all the values will come between 0 and 1. Now you calculate covariance. What happens? All the numbers are going to be kind of close to 0. And then you can actually look at the magnitudes. This process of dividing with maximum value is called as normalization. Okay, in a layman's terminology, fixing scale or normalizing the data. Okay, got it? What is normalizing data? You got it, right? Right? Take the maximum and divide the values is called as normalization. So if you do the normalization using standard deviation, right, that is called as correlation. We are doing normalization here. After subtracting, we are dividing, after subtracting mean from each of the x, we are dividing with the standard deviation and summing it. When you do normalization, right, the correlation coefficient comes between -1 and +1. Okay, as when you actually do take maximum and divide each number here, the column values are actually coming between 0 and 1. Similarly, it is not same. Similarly, when you take covariance and divide it with the standard deviations of x and y, the correlation coefficient will come between 0 and 1. Same thing, whether you do covariance or correlation is the same, but covariance is standardized value and it is going to be between -1 and +1. If the value of the covariance, the correlation is close to -1, strong negative relationship. It will give you direction and strength both. Correlation will give you direction and strength both. Minus negative means negative relationship. One increases, the other increases, and it is strength is very strong on the negative side. Positive one, the close to one means very strong positive relationship. One increases, the other increases. Close to 0, no relationship. Okay, so correlation coefficient actually solves the problem of measuring strength of the relationship. Got it? Any questions there? I took the example of dividing with the maximum to show you that the values come between a range 0 and 1, right? Like that, when you divide the covariance with standard deviations, the value comes between -1 and 1. When you divide with standard deviations, right, you call it as correlation coefficient. Okay. Got it? Any questions? Now you see the relationship correlation between experience and salary is 0.953. Experience and aggressive behavior is -7.9. So it is almost like, it is -8 it is. This is -9.9. As good as this positive relationship, this negative relationship is also. Right? This feature is important. This feature and this feature are also important in making predictions of salary or the experience maybe. We are looking at experience to aggressive. Maybe I should have done salary to aggressive, salary to account activity score. Then I would have seen which feature is important to predict the salary. Any questions so far? I have some more points to explain here. Any questions? Okay. So there are several types of covariance, correlation coefficients. Pearson correlation and Spearman correlation. Okay. So this formula is Pearson correlation formula. Okay. And this is the heat map of all the correlation coefficients. Tomorrow I'll start with the same thing. That's where I'm actually going a little faster. Right. Spearman correlation actually called as rank correlation. Okay. Rank correlation we call it as. What we do is we take the data and calculate the ranks. We take the data, calculate the ranks, and then calculate the Pearson correlation between ranks rather than the original values. Why this is useful? If you look at this data, in the subject 1, the marks are between 1 and 100. In subject 2, the marks are between 1 and 10. The scale is different. When you try to calculate Pearson correlation, the correlation coefficient may not be appropriate. To bring this data and this data to similar scale, we are actually calculating ranks and then calculating the Pearson correlation between the ranks. So that will actually give you more appropriate outcome. Okay, so I'll show that example tomorrow, and there is more to know about the correlation. The correlation is always not causation. When you see the correlation, a number, high number, that may not be right. If you see low number, that may not be right. We'll see when it is and how to actually find out. By looking at visualization, right? We'll see, how to find out. So this topic itself is altogether different one, because I already, took a lot of time in recapping, so I couldn't go much on the correlation. We start with correlation coefficient and cover all these, other things. Okay, these are very important concepts, interview perspective as well as work perspective. I take more preference to work rather than interview, right? But interview is always covered. Okay? Interview thing is always covered. So that's it for today. Any questions you can ask.